Greetings. We are going to look at a quadratic function and determine its domain and range without graphing it. Normally I like to tell students to graph the function that you want to determine the domain and range of because it's easier to see the graph and determine domain and range from the way it's plotted. But I know students don't always like to graph. They either are not comfortable with graphing or they think it takes too long. We're going to look at using algebra to determine domain and range. The first thing that we need to know is the equation for the axis of symmetry for a parabola. That will be an x value, and we're going to take the b value from our standard form. A is the coefficient of x squared, b is the coefficient of the x, and c is the y-intercept. And then a here multiplied by 2. So this is a negative in the formula. So in our case, we have -2 here. The double negatives will force that to be a positive as we plug in values. Let me just label this. In the particular example that we have, 3 is the a value, -2 is the b value, and +4 is the c value. Since standard form is in the positive, this monomial plus this monomial plus this monomial, anytime we see a negative or a subtraction, that is showing that our coefficient carries that sign. I will have x equals -2. I'm adding parentheses to separate those two negatives. 2 times the 3 over here. So again, as we simplify the double negatives, that forces that to be positive. And we have positive down here. 2 times 3 is 6. This reduces to 1/3. Since this is the axis of symmetry, that means that this value will help us determine the local maximum or minimum for this function. We're going to take this and plug it in for x. When we find f of 1/3, this will be the local maximum or minimum for the quadratic. Once we run through the simplification, we find that the f of 1/3 is going to be 3 2/3. This is going to be the local maximum or minimum. How do we define whether this is maximum or minimum? Well, we do that based on the a value. If the a value is greater than 0, then this is a minimum. The reason that is when the a value is positive, we get a parabola that opens up, meaning that the y value here is the lowest y value that's going to be in the range. The axis of symmetry will run right down through the center of this. Then if we have that a is less than 0, we'll have a local maximum. The reason for that is we will have a parabola that opens down when the a value is negative. So the axis of symmetry runs through here, and we will see that this is like a hilltop. So this is the highest y value, and all the y values in the range will be below that. we will not have a equal to 0, because if a was equal to 0, the x squared term would disappear, and this would leave us with a linear function, and it would no longer be a parabola. So these are the two cases that we will have for a. Now that we've identified this, looking back, a is positive, so we have this case. So this is a local minimum. As you can see from my sketch, all the y values will be greater than or equal to that. So in the question of range, we're going to have this value is going to be critical to where the range exists here. I've kind of skipped over the domain. If we look at either of these sketches, we see that the end behavior is either both endpoints are going to positive infinity for y, or both the endpoints go to negative infinity for y. And this is opening up, and it eventually spreads out as it approaches positive infinity in the y direction or negative infinity in the y direction. It is spreading out as it grows up or grows down, and it eventually covers the x-axis, which runs this direction, as it goes to infinity. So it will essentially cover the entire x-axis as it spreads out. Anywhere where we would put a vertical line in here would touch both the plot of the parabola and the x-axis once each per line. So we see this passing of the vertical line test. That is a common thing for testing. If we have a function, it passes the vertical line test, and anywhere that we put a vertical line, we will hit the x-axis and the plot. So this tells us that our domain is all real numbers. And then our range, again, is based off of this value here. Y is going to be greater than or equal to 3 2/3. Again, we are looking, a is positive 3. If a is larger than 0, we have a local minimum, so all of our y values have to be above this value. So we have domain, all real numbers, range is greater than or equal to 2/3. Let's look at one more example of the quadratic function and determining domain and range without graphing. All right, I'm first going to identify my a, b, and c here. In this case, we have a is equal to -2, b is positive 4, and c is -3. I'm again going to plug in my b and a value into the axis of symmetry formula here. X is going to be equal to -4. We had positive here. There's a negative in the formula. We have negative. And then 2 times a value. We had a negative here. I'm going to put that in parentheses so that I can keep those signs separate. So I have 2 times -2. This ends up giving me -4 over -4, which is 1. So my axis of symmetry is going to occur on the vertical line that intersects the x-axis at 1. We're going to use this, plug it into the function. So we want f of 1 and then when we simplify this, this is going to be our y value. Since a is -2 here, we see that we have this condition here. This will simplify to a maximum value, so all of our y values will be less than this. All right, we see that f of 1 is going to be -1 here. Again, this is a maximum, so all of our y values are smaller than this. So y is going to be less than or equal to -1 there. Again, all real numbers for our domain because we have this. The parabola continues to spread out. It will eventually cover the x-axis. We have an onto function here. That's something to note. If we run a horizontal line here, we see that we will touch the parabola twice, and we will do that on either one. So this tells us that we will have at least one x value associated with every y. And in fact, we can have 2 y values associated with every x. So we have an onto function. Hopefully this helps clarify how to find a domain and a range for a quadratic function without having to go through the process of graphing the parabola. Cheerful calculations.